So section 1.4 introduces the matrix equation AX equals B. So we've extended from linear systems to augmented matrices to the vector equation. And the matrix equation is essentially sort of a restatement of the augmented matrix, only with a little bit of vector notation involved. So if we have an m by n matrix A, which has columns A1 through AN, note that a matrix of dimension or size m by n has m rows and n columns. So that's the way we'll read those sizes, m rows by n columns. Then we have A1 through AN as our columns. And if X is a vector in the space Rn, then the product of A and X, the matrix A and the vector X, is the linear combination of the columns of A using the corresponding entries in X as weights. So that looks like this. We have A times X, matrix times vector. We write the columns of A down, A1 through AN, in this vector notation, and multiply it by this vertical vector x1 to xn, or this column vector. And that matches A1 to x1, A2 to x2, and so on down to AN times xn. So we have this linear combination of the columns of A with X as the weights. So that is our connection to vector equations, right? So this is a matrix product between a matrix and a vector is a linear combination of the columns of that matrix using the vector as the weights. So our first example is to write the given system of linear equations as a vector equation, then as a matrix equation. So we're just going to transform a system of linear equations into first a vector equation, then as a matrix equation. So remember the vector equation looks like we have x1 times the vector of its coefficients, x2 times the vector of its coefficients, and x3 times the vector of its coefficients. And that's all equal to the right-hand side, or the vector of the right-hand side. So our solution here is that our vector equation be written as we did in the last section. And that is x1 is the weight times 2, 1, and 3 are the coefficients of x1 in each row respectively, and then plus x2 times each of x2's coefficients, 1, -1, -2, and then plus x3 is -3, 1, and 0. And all that's equal to the right-hand side vector, which is -4, 3, 1. -4, 3, -1. So there's our vector equation. We could put a box around that, but nonetheless, it's labeled. That's what they're looking for there. They don't ask us to solve anything. They just ask us to rewrite the system first as a vector equation and then as a matrix equation. So as a matrix equation, we would write it as follows. It'll look like the augmented matrix times the vector x, and that's equal to the right-hand side. So I'll have 2, 1, 3, the coefficient matrix, I should say, rather. 1, -1, -2, -3, 1, 0, times the vector x, which has components x1, x2, x3, and that's equal to -4, 3, -1. So this all matches our definition from the previous page too. The transferring from here to here between these two equations, we're using the definition on the previous page. This is, of course, AX equals B. Look at the way this is written, and the way that breaks apart is in this vector equation, x1, A1 plus up to xn, AN, oops, x is a scalar, equals B. So that's the vector version, and that's what's written in the vector equation above. If we wrote out each of the columns of A, and we'd have exactly that, and wrote down what B was. So those are the two components. In fact, maybe I'll place this in their respective spots here, and this one will sit below to kind of indicate the vector versus matrix equation. Now they're equivalent, right? They're both going to result in the same solution, and that's actually stated below. It's kind of easy to see that. It's just a matter of notation, writing these things out. Since this is equal to this, then of course you're going to have the same solution, or is equivalent to that, I should say. So, or essentially this is defined as this, which is again where that equivalence comes from. So it follows that the result in this theorem here, if we're given an n by n matrix A with columns A1 through AN, and if B is some vector in Rm, then this matrix equation has the same solution set as this vector equation. So that's a nice fact to have. And having that established, we'll sort of, I'll write out the details for a theorem that summarizes this result, along with another result or two added to it at the end of this section. So another connection that this makes as well is that the solution to this system and this system is the same solution for each, and as well as the augmented matrix A1 through AN with B augmented to the end of that matrix. So these are all essentially the same systems. This is what's been asserted all along, and it's just a matter of kind of carrying out the written details to prove that that's the case. I think it's probably sufficient to work enough of these problems, actual examples, to realize that yes, if you find a solution to the vector equation or the matrix equation, you're also finding a solution to the augmented matrix, which is equivalently the linear system of equations. So a lot of interchangeable parts. These are all different ways of looking at the exact same thing. So as far as existence of solutions goes, we have a result which follows that the equation AX equals B, the matrix equation, has a solution if and only if B is a linear combination of the columns of A. Well, let's go back. That's really just a deduction of the previous result. AX equals B as a solution if and only if B is a linear combination of the columns of A. Well, if these two things are the same statement, then if the first one, AX equals B, has a solution, well, then that means there's a vector X such that this is equal to the right-hand side. This linear combination is equal to B, and that's exactly what this result is saying. B is a linear combination of the columns of A. And then vice versa, if B is a linear combination of the columns of A, well, then we're going this direction and rewriting that as AX equals B. And of course, those were defined to be equal on the previous page. So we can use this fact in a pretty useful way. And we'll see this below. So what we'll do is we'll be able to answer questions about whether or not a solution to a system could exist, and in what capacity it does exist, right? In what conditions it will exist. So the question this example asks, after we let A be the given matrix and B be a three tuple or a three component column vector, B1, B2, and B3, they ask, is the equation AX equals B consistent for all possible B1, B2, and B3 values? So in other words, will we have a consistent system, or we have a solution for this system, one or more, right, for any possible combinations or values of B1, B2, and B3. So let's see if we can use what we know already in order to answer this question. So let's write the augmented matrix 1, 0, 2, B1, 0, 1, 3, B2, negative 1, 1, 1, B3. Now, why have I written the augmented matrix? Well, it's because I'm thinking about AX equals B, right? What we're concerned about is whether or not this is consistent. Right? In other words, does it have one or more solutions? Is it not inconsistent? Just the other way to think about it. Well, consider that the only way for this system to be inconsistent is if we have a non-zero element here on the right in any one of these columns on the right-hand side and all zeros leading up to it. Okay, in other words, our pivot position is in our augmented column, right, our rightmost column. That would be a problem. That would be asserting that 0 is equal to a possibly non-zero value. So in order to find whether or not this is a consistent system, we need to put this into row echelon or possibly even reduced row echelon form, and then see whether or not there is a pivot position in this column. If there's a pivot position in the rightmost column, then we're in trouble because there will be a row of zeros preceding that, and then this value, whatever it is over here, won't be allowed to be 0. So that's a description of where we're going to land, but let's get there and then interpret the result. So in the interest of reduced row echelon, let's add, let's rewrite row 3 as itself plus row 1. So we have 1, 0, 2, B1, 0, 1, 3, B2, and we're adding row 1 to row 3 because we're trying to get rid of this -1. We're zeroing out the column below our top rows leading 1. So this becomes a 0, 1 and -1 is 0. 1 in row 3 adds to 0 and we get 1. 1 and 2 is 3. B3 and B1 is B3 plus B1. Okay, we'll just add up the right-hand side as it comes. They're of course, they are unknowns, more or less, but they're still going to change per whatever row operations we make on this matrix. Now our next leading one is here. We need to 0 above and below it. Well, so we only have one task. We need to 0 below. So we'll do row 3 is equal to itself minus row 2. And we see pretty easily that when that happens, row 2 is still as it was. We have 0, 0, 0, B3 plus B1, and we subtracted row 2, so this is minus B2 here. And we landed this position. We're in reduced row echelon form. Leading ones, our pivot positions are here. Now, okay, maybe we're not quite in reduced row echelon. This might not be a 1, but what we can see is that we have a pivot position in the rightmost column in the augmented matrix. That's a problem because we could choose values of B1, B2, and B3. Namely, I could say this, let's let B1 be 1 and B3 and B2 be 0. If that's the case, then we have 0 plus 1 minus 0. And that's a choice for B1, 2, and 3 that would not allow this system to be consistent. We'd have 0 equals 1, right? So AX equals B is not consistent for all B. There are some choices of B, namely the choices for which the system is consistent is when B3 plus B1 minus B2 is equal to 0, right? That ensures consistency. So let me write that. But that's not any values of B1, B2, and B3. That's a constraint. So it's not true that it's consistent for all values. Since we can choose B1, B2, and B3 such that B3 plus B1 minus B2 equals 0. And there are infinitely many choices that would work here, but I'll just demonstrate one random decision we can make, and that would be B3 equals B2 equals 0, and B1 is equal to 1. Okay? If B3 and B2 were 0, then 0 plus 1 minus 0 would be 1, and it would no longer, this is non-zero, it would be non-zero. And if we have a non-zero value right here, then we have an inconsistency, 0 equals 1. Right? So there are choices for B for which the system is not consistent. But notice the way we arrived at this is we took the augmented matrix, put it into echelon form or almost reduced row echelon form, and then made our analysis from there. Consider the row reduced version of this matrix, and we're able to do quite a bit of work there without really having to dig too deeply into this system. We can see, given this situation, we can answer what seems like a complicated question quite easily just by using the row reduced form of the augmented matrix. So yeah, it's not the case that for all values of B1, B2, and B3, there's going to be a solution. And that's namely because we had a row of zeros here. Now, had we arrived at a row reduced form of this matrix where all our leading ones or all of our pivot positions were to the left of our rightmost column, then we would have a consistent system. So as long as there's no zeros leading up to our rightmost column, then we could have a consistent system. It would have worked for all B1 through B3. So keep that in mind for examples that are similar but with different results. So one of the primary results in this section is this set of equivalent statements right here. Now I've sketched the proof, but I won't drag the viewer through this. If you wanted to pause this and read through and see all the notation that's being carried out. Essentially, the way you prove equivalence of a list of statements like this, just for an idea of the logic, is you prove that if A is true, then B is true. And then you prove that if B is true, then C is true. And then you prove that if C is true, then D is true. And then you prove that if D is true, then A is true. So if you can get each one of these statements to imply the other one, and you can do that in a loop so that D implies A, well then D implies C, and C implies D, and D implies B. Everything implies everything else because of the loop. So if we thought about it as a chain of arrows representing our implications, we could move along the implications to here, and we'd have all of these things as equivalences. So the book actually shows this equivalence. They show that A implies D and D implies A. And I'll leave the reader to look at the book's proof of that. It's actually one of the most important proofs, parts of the proof of this theorem. What I prove below is just the intermediate steps of A implies B, B implies C, and C implies A. So I've got equivalence below for A, B, and C, right? If we needed to show that C implies B, we could realize that C implies A and A implies B, thus C implies B. There's a transitivity property that holds there logically. Now, in the book proves that A is equivalent to D, and then that closes the loop on all of it. If you set these things up with these 2 and 1-sided arrows for implications, you'll see that all of this does completely show the equivalence of each one of these statements. So 2 statements are equivalent if they each imply each other. In other words, A is equivalent to B means A implies B and B implies A. So just for a little breakdown of logic, we're going to use this. We're going to see a lot of theorems that use these equivalences in addition to just implications as well. So knowing how these things are proved and how they come about is a worthwhile aspect of the course. So again, like I said, A through C is just a matter of writing the notation out as I've done in previous parts of these notes in this section already. This is just sort of a recap and a bit of a repeat of the things we've already done in previous problems or sketches of proofs for other things, for other results ahead of this. To end the section, let's talk about the row vector rule for computing the product of a matrix times a vector. So if you've ever done matrix algebra or matrix vector algebra, you already have an idea of how to compute the product of a matrix and a vector. And what we've just defined at the beginning of this section was a little bit different than what students might be used to. And I believe no other textbook really does what this one does in terms of that definition, which is helpful to connect it to the linear systems. But pretty much everywhere you look, you'll see this definition of matrix and vector products. So let's have a look in there. We've got, if the product AX is defined, in other words, the dimensions match up correctly, we'll talk about that later, then the ith entry in the product AX is the sum of the products of corresponding entries from row I of A and vector X. So row I of A times the vector X, corresponding entries. This is the first, second, third entry of A times first, second, third entry of X. Okay, so this is the matrix product you're probably used to if you've seen one before, and it's just as well to compute with it as it is to use the linear combination spoken about at the beginning of this section. Only the one at the beginning of this section is more useful for connecting this theoretically to the linear systems. So this product now, the first component will be 1 times 5 plus 0 times -2 plus 2 times 1. The second is, so the second row of A times X is the second element, and we'll have 0 times 5 plus 1 times -2 plus 3 times 1. And if we were to write this out and identify the columns A1, A2, and all that for the matrix A, we'd realize that this is in fact exactly what we defined at the beginning of this section. The third is the third row of A, all of its components times each corresponding component at X. -1 times 5 plus 1 times -2 plus 1 times 1. And the result of this is just to carry out these products and sums. We have 5 plus 0 plus 2 is 7. We'll have 0 minus 2 plus 3, so -2 and 3 is 1. And then -5, -2 is -7, plus 1 is -6. We arrive at this vector. Now the question is, how did we know that we should arrive at a 3x1, 3 rows, 1 column matrix, i.e. a 3-tuple or a 3-dimensional vector? Well, this is something that we'll look at a little bit later on, but notice that this matrix dimensions are 3 rows by 3 columns, and we're going to multiply it by a vector with 3 rows and 1 column, or a matrix of 3 rows and 1 column is a way to think about a vector. And the inner dimensions match. That's what helps with the definition. There are as many elements row-wise as this has column-wise. Otherwise, say there were 4 elements here in the row of A times the 3 elements in X, there wouldn't be a multiple for the 4th element of A in that row. So it wouldn't be defined. So in other words, what would happen in that case is this 3 right here would be a 4, and the inner dimensions wouldn't match. When the inner dimensions don't match for a product here, then the product's not defined. When they do, it is defined. And the inner dimensions sort of fall out, and the resulting dimension is the outer dimensions. This 3 and this 1 give us the dimensions of the result. So that's a nice way to look at it. So if we look at the next example, we've got this product. This is a 3x2, and we're multiplying by a 2x1. So our result should be a 3x1. The inner dimensions match, so they'll fall out, and we'll end up with a 3x1. Let's see if that's the case when we carry out the product. So 0 times -2 is 0. 2 times 1 is 2. So that's this row times the column, corresponding entries. 1, 3 times -2, 1. So we have -2 plus 3. And then we've got 1, 1 times -2, 1. So -2 plus 1. And this turns out to be 2, 1, -1. And there we are. a 3x1 vector, 3 rows, 1 column, or 3x1 matrix, I guess I should say. And we'll talk more about matrix dimensions and sizes later on, but this is nice to know ahead of time. It's an easy little rule of thumb, but we'll define things to make it formal later. So here's the result about matrix vector multiplication. So if we have an m by n matrix A, and we have two vectors u and v and Rn, and then some scalar c, well then A times u plus v is equal to A times u plus A times v. This is nice. This is a distributive property for matrix multiplication. And this is a scalar multiplication property for matrix multiplication. Both are proved in the textbook, but I'll just give a demonstration of, or a sketch of the proof of B. It's a little bit shorter, and it'll be a good launching point to sort of see how these proofs are constructed. Now, A times C u, u being a vector and A being an m by n matrix, and u of course is an n vector. So C times u is a scalar multiple C times the vector u. We write the vector u as u1 to un in column form, and then C times each of these times this vector is C times each component. C times u1 plus C times u2 all the way down to C times un, and that's still an n vector. So remember that the matrix product A with a vector is the linear combination of the columns of A using the vector entries as weights. So A1, the first column of A, has CU1 as its first weight. And that's true for A2 and CU2, all the way down to AN and CUN. I've actually got a typo that I just picked out right there. CUN is right there. Good. I think the rest of these are fixed. Now, once that's written down, this line here, we can factor C away from this. This is just a linear combination of A1 through AN. Everything has a multiple of C in it, so we factor it out. And we've got now this linear combination of A1 through AN, the columns of A, using U1 through UN as the weights. That's exactly the definition of A times the vector U1 through UN. And that's just A times U as a vector, and C is times that. So we've arrived at the right-hand side of B. Okay, this is easy to see. If maybe, for example, you might want to try write down maybe a 3x3 matrix A. Any numbers will do, and then write down a 3x1 vector U with any numbers in it, and then take some constant C, multiply C times U, and then do A times that resulting vector, and see that it's the same as multiplying A times the vector U first, and then multiplying the result by C. That's a way to not prove, but at least confirm what this theorem states. But these are just basic properties of matrix vector multiplication that'll be useful to us later on. So that's it for section 1.4. Of course, the examples will be a little bit more numerical than just these proofs. So you'll have something to really get some practice with. So be sure to jump into those problems. And most things should look more or less like problems like this, but connect to any theoretical questions that you can with this.